Yeah, so this will describe the sort of credibility of this trader, right? Should we believe this trader? And of course, if you're 10 out of 10, then you're perfect. So we can trust you a bit more. How do we describe that trust? And that is this little matrix here, all right? These four numbers here. So if you recall, your conditional probability says, given that S1 has happened, S1 has happened, what is the probability that the consultant says S1 will happen? Because remember, I1 is the event that the trader utters the words S1 will happen. So that what's the probability that the trader, the consultant, says S1 will happen? So that is essentially, given that the Dow Jones has gone up 10 times, how many times did the trader predict before each day, each of those times, that the Dow Jones will go up? So we are counting the up triangles divided by the total up arrows. So that's 8 out of 10. Can see that? All right, so that's a way to describe it. And of course, how many times, given the S1 again, so given all the up arrows again, 10 of them, how many times trader made mistake? In the sense that he said S2 will happen, Dow Jones will go down, but eventually it was known that Dow Jones went up. So that is going to be 2 out of 10. Yeah. Okay. So you see how we can actually gather these four probabilities, these four conditional probabilities, like a CV, like the credibility matrix of this consultant. Now, again, let me stress again, the consultant, I said trader here because we're comparing with Dow Jones. It could just as well be a AI program. So you ask the program, uh, tomorrow Dow Jones will go up or down. And it says up. Tomorrow Dow Jones will go up or down, up, down, right? So we can count and then divide by the total ups. So given the probabilities of S1 and S2 happening, so this is the prior probability. How do we get that? You can go back 100 days, and out of the 100 days, Dow Jones would have gone up, down for the 100 days, right? The 100 trading days. And you count how many ups, the up arrows divided by 100, that would give you P of S1, P of S2. So that's like the rough assessment of um, whether Dow Jones have been up in the major sense. Like most of the days it went up, it closed up and up and up, and then a few days it went down, right? Again, we are disregarding the magnitude. You can go up by 1 point and then drop by 1,000 point, right? But let's just disregard that and just talk about up and down so that we have S1 and S2 defined clearly. So we have the prior probabilities. Now that we understand that, we have the prior probabilities, that's P of S1, P of S2, prior to asking the consultant. Yeah. So the consultant is described by a set of credibility matrix like this, which is given S1, given S2. Yeah. So notice this very, very nice symmetry here. Given S1, given S2. Remember, S1 and 2, they are states of nature, not controllable by the decision maker, right? So S1, S2, given, what are the probabilities of consultants saying S1 will happen, saying S2 will happen? Okay, now again, let me just do a quick reminder. I1, I2, for simplicity of understanding it, I say I1 and I2, they are defined as consultant uttering the words, making predictions that S1 will happen. Also, that's I1. If a consultant, in the event consultant says S2 will happen, so that event is called I2. Because what consultant says doesn't mean reality will be the case. So that's nice here, because Bayes' theorem actually now allows for a predictor to be wrong, to be possibly wrong, to be probably wrong. Yeah. So that's very interesting, because now we can describe in probabilities how likely is this consultant, is this device, is this program going to be wrong. Yeah. Now, given these 6 numbers, okay, so those are the inputs. Those are the inputs. Bayes' theorem allows us to calculate the posterior probabilities after, posterior means after, consulting this consultant. After hearing from the consultant, what is our new probability, so to speak? Okay, now let's look at what that means first. Posterior means after consulting the consultant. notationally, you see that this is given that I1. So it's now reversed. S just now was all the inputs were given S1, S2, S3, S4, S5. Now Bayes' theorem reverses the role. Instead of given S1, S2, we can derive the probability of S2 happening given I1 has occurred. Remember what is I1? I1 is this consultant, this expert, saying S1 will happen. Okay, now let's think about that. A consultant that we trust, that we find that this person has got a lot of expertise, says Dow Jones will go up. Would you start to grab the shares now because expert says Dow Jones will go up? You will start buying the index, right? So you might buy first because expert, very reliable, credible expert says Dow Jones will go up tomorrow. Won't you start buying now? Yeah, so that's the idea here. When this consultant utters the words, S1 will happen today, right now, what's the chance that S2 will happen tomorrow? Well, the tomorrow, we didn't say that the probability, remember, when you say probability, is going to be future or unknown state. So what's the chance that Dow Jones doesn't go up? So in other words, what's the chance that the expert made a mistake? Right or not? In the sense that the expert already stated it will go up. I'm pretty sure I'll sign my name on it. And then what's the chance that the other side happens, S2 happens instead? So when we ask this question, hopefully the result is a small number. Then the chance that the expert makes a mistake is going to be low, meaning we can trust the prediction. Yeah. So now that we understand that Bayes' theorem essentially, all right, given the 6 numbers, essentially reverses the conditional probabilities from one that is given S1, S2 happened to one that is given I1, I2, I3 has happened. Now, why is this useful? In applications of Bayes' theorem, oftentimes it is important to predict, forecast the future, right? To know the chance of happening. And if this chance is high, it can tilt us towards believing or changing our action, right? So if the chance, if in our own assessment is 50-50, then we are not so sure. And even if we commit, we are like, phew, luckily we were right. So the process of doing it is not so assured. But when we consult an expert and the expert utters I1, yeah, and then we ask, what's the chance P of S1 given I1? What's the chance that the outcome S1 is exactly as what the expert predicted, I1? And if this number is 0.82 instead of 0.5, then we say, wow, okay, I think we can take a chance because it's a calculated risk, right? Chance is chance. It could still mean that we can be wrong, but then with a 0.82 versus 0.5 originally, we would trust that our decision, even if the outcome is not as expected, we trust that the whole decision process is correct. Okay, that's one. So prediction is one big application of Bayes' theorem. The other application of Bayes' theorem is, in a way, also prediction, but more because it is difficult to impossible to directly measure and count the occurrences of P of S2 given I1 or P of S1 given I1. Anything that's given I1, I2 is impossible or very, very difficult or very, very expensive in practice to gather. All right. But it is way easier or at least feasible or cheaper or faster to gather probabilities like this. Given S1, what's P of I1? Given S2, what's P of I1, I2? Yeah. So because the conditional probabilities done this way is easier to gather, but what we really want is, the other one, the flipped over conditional probabilities. So what do? We gather all these numbers and use Bayes' theorem to flip them. So that would be another big applications of Bayes' theorem. So for example, in certain medical examination, maybe even COVID-19 R&D development, it is perhaps at the initial phase of COVID-19, right? Very difficult to get the cause of death or the possible spread. I mean, what's the mortality rate? I mean, how likely is the virus going to kill people? So it is very difficult, and sometimes you cannot be purposely injecting people with COVID-19 and see whether the person dies or not, right? So very difficult, and you have to wait, and time is of essence. And so so sometimes it's much easier to carry out experiments in the sense of gathering P of I1 given S1, P of I something given S something, and then reverse back to get the other conditional probabilities. Right. So these are the two major applications of Bayes' theorem. So when we extend to higher divisions of subsegments, the calculations is just done the same. Just Bayes' theorem allows us to easily convert the conditional probabilities, flip them backwards, and because of that, mathematically it's just flipping, right? But in terms of actual applications, tremendously useful, right? For one major class of applications, predictions, forecast, assessment of the likelihood of happening. And another major class of applications, one way to get conditional probabilities, very easy, cheap, ready. The other conditional probabilities, when we flip it around, is really what we want, but very expensive, impossible, takes a long time to gather with any sense of accuracy at all. Yeah, so that's the reason why we really like Bayes' theorem a lot.